Patty. I'd like to welcome everyone. My name is Dan Stansel. I'm head of the Electrical and Computer Engineering Department. And on behalf of the department and the Freedom Center, I'm really delighted that all of you were able to come on a rainy Friday afternoon. And I think the crowd that is assembled here in the presence of the rain is testament to the draw of our speaker today. As you know, and I appreciate many people from ABB coming today as well and joining us. It's always delightful to have our colleagues here. As many of you know, ABB has been a strong partner with the Freedom Center for quite some time. And recently, there have been some additional gifts that we're very appreciative of, including funding for some professorships and scholarships. And one of the items was funding for a new seminar series. So I'm happy to have this first kickoff session for the ABB Distinguished Lecturer Seminar Series. And pleased that you all would be able to join us for this. And for our first speaker, I'd like to introduce to you Mr. Gary Rackliffe. Gary was appointed to Vice President of Smart Grids North America in May 2009, and he leads ABB's Smart Grid Initiative in North America, including business development, strategic partnerships, and ABB's marketing and product strategies. Gary has over 25 years of industry experience in both transmission and distribution, and has worked for ABB for 18 years in Raleigh. He was previously the Vice President of Marketing and Sales for the Northeast and Mid-Atlantic sales region, covering ABB transmission and distribution equipment, power electronic products, systems, and services for the utility, power generation, and public power customers in the region. Other positions include Vice President of Strategic Marketing for the Power Products and Power Systems Division in North America, and Vice President of Marketing, Sales, and Business Development for ABB's Network Management business. He also directed ABB's Flexible AC Transmission System business for the U.S. Gary holds MS and ME degrees in Electric Power Engineering from Rensselaer Polytechnic Institute, and I discovered that we have something in common and that we both spent some time at Carnegie Mellon. He received his MBA from Carnegie Mellon. He's a member of the GridWise Smart Grid Implementation Committee, the Distributed Advisory Committee of the NEMA Smart Grid Council, a senior member of the IEEE and the Registered Professional Engineer in the Commonwealth of Pennsylvania, and he's the co-author of a book on transmission and distribution planning and has published several technical papers. So it's my pleasure to introduce Mr. Gary Rackliffe for our initial ABB Distinguished Lecture Series.
Thank you. Okay, good afternoon. Dan, thank you for the introduction. What I'd like to do today is hopefully give you some background on what is smart grid, what are utilities doing in the smart grid area, what are drivers behind why this is so important to the electric utility industry, and in some of the challenges and also some of the technologies that are being implemented, and provide that at a little bit more detail. By the way, I appreciate the students who talk to me. There's only 3 ties in the room, so we sort of kind of stand out a little bit. And I was told no students would talk to anybody who had a tie on. But anyway, this is an overall landscape that shows some of the key elements of the smart grid technologies. I think what's interesting with smart grid, it really is an evolution as to how we generate and deliver energy. Instead of being all centralized generation and then pushing that power through a transmission and distribution system to end users, we're now changing that paradigm. We now have distributed generation, we have distributed energy storage, we're introducing electric vehicles, we're introducing utility scale renewable and utility scale energy storage, and the whole landscape is dramatically changing from what it has been historically. So what I'd like to do first is go over what we see as the 5 drivers behind smart grid. And this is a global perspective. So this is a slide that actually was initiated out of our Zurich group, but it's directly applicable to what we're doing here in North America. So there's capacity, particularly when we talk about electric vehicles and some of the economic growth in India, China, and now we're seeing that in South America. There is a growing need to also add capacity to the grid, and there's reinforcement of that infrastructure. Reliability is a big issue. Again, most outages, as seen by the end-use customers, occur because of a problem with the distribution system, whether it's a tree falling on a line, pole car incident. Most outages do occur as a result of distribution, but we have also seen major outages occur. For example, the one that occurred, I think it was in 2003 across the Northeast, obviously was initiated by transmission. Energy efficiency, I have a slide that shows that we're not very efficient when we look at the prime energy that goes into the conversion process of fuel to electricity, and then how much of that is actually used at the end-use customer. I have a slide that I'll go into why efficiency is so important, and there's two elements. I will show the loss of the energy, which is one element of efficiency. There's another element of efficiency, which is how we deploy the assets that deliver our energy. We build the assets for the peak load, but peak load doesn't occur very often. Well, it occurs every day, but only for narrow bands. So we have all this excess capacity which we build into our systems, which ultimately is not a terribly efficient use of those resources. Sustainability, one component of the smart grid is the interconnection of renewable generation. Major element of what we're trying to do with the smart grid and how we manage these renewable resources. And then finally, customer enablement. There's been a big buzz around smart meters and how smart meters, I think most people, anybody who's familiar with smart grid in terms of outside the industry, have associated smart grid means smart meters. Now, can anybody here tell me when the first smart meters were implemented? Anybody want to venture a guess?
79.
Not quite that early. It was the early 90s when solid state meters were introduced for commercial and industrial customers. So most commercial and industrial customers in the United States have had smart meters for more than 20 years. The big news is now we're taking that same technology and we're moving it to the residential customer segment. What's interesting is customer enablement. There were some assumptions made. If you put a smart meter on a customer house, they'll actually do something. And again, not really a good assumption, as some utilities have discovered. And there's been some backlash against smart meters, particularly PG&E has got some lessons learned about what not to do. You don't change rates. You don't put smart meters out right before summer peaks and then expect people to not be sensitive to changes in their bills as a result of having a new meter technology. So a little bit more detail on those four areas. This shows forecasts. This is from the International Energy Agency showing forecasts from 2006 to 2030. So when you see a 31% growth in electricity consumption, don't get too excited. That's only about a little over 1% a year. What's relevant, though, is you see the shift that has occurred between overall energy consumption, which is shown on the arrow on the left, and that consumption which is based on electricity. And in the more developed areas of the globe, specifically Europe and North America, you can see it's about a 3-to-1 ratio. Now when you look at China, you can see far greater energy growth, more of a 2-to-1 ratio. Same thing similar in India. And then when you get to the Middle East and more specifically Africa and also South America, you can see that particularly for South America, it's approaching a 1-to-1 relationship. The core message here is as economies and as countries become more developed, there's more focus on electricity consumption as the energy end-use method, and so we see the need for greater capacity in terms of electricity delivery. When we talk about a reliable grid, I mentioned at the distribution level, that's probably the source of most of the outages that do occur. So there are techniques in terms of managing the distribution system. There's outage management systems. And now the technology is being developed and deployed for fault detection, isolation, restoration. It's also called FLISR, which I believe is fault location, isolation, and service restoration. But regardless of which acronym is used, it's basically clearing a fault when a fault occurs on a distribution system, isolating that fault or the faulted section of the circuit by opening a device which is on the customer or load side. So you now have isolated the section of the circuit where the fault occurred, and then you connect normally open switches or close normally open switches so you can re-energize those customers who were connected to the feeder where the fault occurred, but on the undamaged portion of that circuit. And that can be done automatically. So you're talking about doing that in less than 5 minutes, which is the threshold between, in the industry definition of what is a momentary outage. If it's less than 5 minutes, it's considered a momentary. If it's greater than 5 minutes, it's considered a sustained. So that's what that process is for FDIR. Asset health. Particularly with transmission assets and transformers, the average age of a power transformer in North America, in the US, is approaching 40 years, which is about the expected lifespan of those assets on the utility grid. The other challenge that utilities face with this large portion of transformers that are getting old is the workforce that they have to maintain those assets. They're even older than the transformers. It's forecasted, you guys laugh, but it's forecasted, unless you guys start to go out and maintain the transformers, it's forecasted that about 50% of the utility workforce will be able to retire over the next 5 years or so. So, a huge challenge for utilities. They got old equipment, and all their expertise on how to maintain that equipment and keep the performance maintain the performance of those assets is going to be walking out the door. So the challenge is how do you manage the assets? How do you make sure that you have notification if there's any operational impact? Do condition-based maintenance instead of time-based maintenance, and then have the information needed for life cycle management. And then the other area is transmission grid management. You probably have heard about wide area monitoring, synchrophasers, big buzz in the industry about that. The value of that information is what you can do with it when you integrate it into a SCADA EMS or energy management system. So you can look and detect power oscillations on the grid. You can improve state estimation by having better data and more up-to-date data. In some respects, I went to a conference one time and they described the way we operate our grid. It's like trying to drive down the road, looking in your rearview mirror with 5-minute-old data giving you your visualization. So with wide area monitoring, you get obviously more up-to-date information. We're still driving down the road looking in the rearview mirror, but at least we're doing it with more up-to-date information. And you can also use wide area monitoring to operate the grid a little bit closer to the voltage stability limits. For those of you who are power engineers in the audience, when you look at the nose curve for voltage stability, if you have synchrophaser data, which is, again, you get more data and it's more up to date, you can better manage your operations. The other, voltage stability, and then of course integration of renewables offers challenges, and I'll talk about that a little bit later. So this is the slide that I mentioned in terms of efficiency, where 80% of the raw energy that goes into the energy conversion process in terms of prior to transportation, but generation is where you start to lose a lot of that energy. And then at the T&D level, it's about 6 to 10%. A lot of that occurs at the distribution level, and a major contributor to those losses are inefficient distribution transformers. So the core losses and the load losses associated with distribution transformers. And that's why the Department of Energy has implemented standards to lower the core losses in distribution transformers, but at least half of that is related to the traditional type of pad mount and pole top transformers that you see along streets or in front yards of homes. The other part, another major component is what are known as reactive voltage losses on feeders due to motor loads, which are inductive loads, as well as the inductance associated with the lines themselves. And so volt-var control and conservation voltage reduction are strategies that utilities are implementing today to lower those losses, typically saving, they can lower losses in the range of 4 to 5%, which again, frees up some of the capacity in the grid and also reduces the generation requirements. And then improving the productivity, we're doing work with drive and high efficiency motors, and then also looking at building management and even home management solutions to improve efficiency at the end use level. Sustainability, this just shows a chart out of again, the International Energy Agency. One of the challenges we have here in North America is we pretty much have built out all of our hydro capability. So we're seeing more wind. North America is the #1 location in terms of overall wind potential, and then biomass, and then solar and other. Just as a point of reference, anybody know, and even the ABB people, you can chime in as well, anybody know what is the #1 country in terms of solar energy development as a percentage of overall delivered energy? Okay, I did hear the right answer. The right answer is Germany, with Spain probably catching up or surpassing. Now, does anybody know what the latitude of Germany is? It's probably about on par with Maine or somewhere in that range. So it's relatively far north. So why do you think Germany leads basically the world in terms of solar deployment? Policy, exactly right. It's amazing what you can do with tax incentives and government policies. But we're seeing solar being implemented here, particularly solar PV on distribution feeders. A lot of it is going into warehouse on rooftops. People are actually selling access to rooftops for solar purposes. And then we're seeing residential deployments also of solar PV. A lot of wind development also taking place. There's actually some projects which are now being considered off the coast of North Carolina. I think there's a couple of 300 megawatt projects that are now being considered. Of course, a lot in Texas and some of the other states. Then the last driver is engaging the end-use customer. A little bit of a difficult or a busy chart here. The lower half is demand response, and load control and demand response has been around for some time. Co-ops and municipals implemented these technologies probably 20 to 30 years ago, controlling air conditioning systems and controlling electric hot water heaters to lower the peak load. So that's what direct load control is, shown in the bottom part of this chart. Some of the other things under incentive-based demand response are programs that commercial and industrial customers would participate in, being able to drop load on an emergency basis, or interruptible programs that they would engage with the utilities in. At the top is price-based demand response. Now again, commercial and industrial customers have had demand meters and time of use rates for 20, 25 years. The thought is, if we put one of those meters on a residential customer, they'll jump up and say, I want to be part of this too. And that hasn't happened. There have been some pilots with time of use rates or critical peak pricing, but for the most part, the average homeowner or residential customer has not embraced the concept of price-based demand response. So that's an educational challenge for utilities to work with their customer base, to make the incentives appropriate so that people want to participate in this. And the real driver on this is being able to reduce the utility peak load and to be able to control that. If they can control peak load, they need fewer T&D resources, they need less generation capacity, and there's economic benefits to do that. There's some benefits for the consumer as well, and I'll show a chart that a little bit later that follows up on that. So those are the 5 drivers. So I want to shift gears and talk now about how utilities implement smart grid. And I'm going to break this into six major categories. So this one being the first, which is information technology. These are technologies that utilities are implementing as enabling infrastructure for the smart grid. And so there's a lot of acronyms up here. CIS, Customer Information System. These have been around. These are basically, this is how the utility issues its bills. Communications. Communications is the principal enabler for a lot of the smart grid technologies. Most utilities are implementing communications on at least a 5-tier structure. So you have the enterprise application bus, the IT system that ties these core systems together. You have communications to substations. Most utilities today are implementing fiber optic communications now to their substations and upgrading their communications. GIS, in this particular presentation, this is Geographic Information System. This is the mapping of all the assets and how they're connected. We use that information to determine the impedance data and the connectivity models for running load flows and other assessments. Asset management, this is the supply chain function for working on the assets of the utility. Work management is managing the people who are working on those assets. Mobile data is how you communicate to the workers. And in security has two elements. For smart grid, it's more focused on the cybersecurity issues because of the technologies that are being deployed, but there's also a physical element to security. But these are what I view as a core and enabling smart grid technologies. These are the core applications, and these are not necessarily listed in any order or priority, and utilities have taken different approaches in terms of implementing these technologies. With the government, the DOE, ARRA funding, the stimulus funding, a lot of utilities focused on AMI to try and get the smart meters deployed. The government was paying for half of those projects. And there was a lot of focus on AMI infrastructure. So that AMI is basically the smart meters. There's other parts to it. There's the communications part. I was talking about the communications in the 5 layers. I guess I didn't go through all 5. Once you get to the substation, then you have wide area wireless broadband, which is typically used for distribution automation and also AMI data backhaul. Then you have local communications, radio frequency mesh networks, which are typically used for metering purposes. Then utilities are now looking at bridging the meter and getting into home automation networks. And then also at the substation level, you have intra-substation communication. So you have those multiple tiers of communication. But AMI does have typically radio frequency mesh communications. There is some power line carrier and other technologies which are used. There's a data backhaul. Could be a public carrier such as AT&T or Verizon, or a utility-owned communications where they use WiMAX or some other technology to do the data backhaul. And then meter data management, where you do the verification, the validation, and the estimation function on the meter data. Distribution grid management. This is a core area of investment which is gaining momentum with utilities. It's also where utilities can drive the benefits in terms of reliability and efficiency. So there's a lot of acronyms on this line. The DSCADA is the Distribution Supervisory Control and Data Acquisition. DMS is distribution management software that goes into the control room for modeling and managing the distribution grid. Applications that typically sit on that DMS software platform include outage management, the fault detection, isolation, restoration that I mentioned previously. VVO stands for Volt-VAR optimization, or there's also deployments for Volt-VAR control where you have a deterministic solution rather than an optimal solution. And other advanced applications include things like revenue enhancement, which is a utility term for detecting and reducing theft on their distribution systems, load allocation, load balancing between feeders and those types of applications. The bottom line is some of the technologies that are out more in the field in terms of distributed software in substations or at the feeder level, feeder automation, This is the automation of reclosers, distribution automation switches, capacitors, and that apparatus which is out in the distribution system. So you have sensors, communications, obviously to drive the solution. Asset health, this is the end-to-end solution to maintain the assets using condition-based maintenance and drive lifecycle management. I talked about that briefly previously. So it's sensors and monitors in terms of the equipment, communications, substation automation, gateways to move the data, the asset data from the substation, analytics, performance models, dashboard, and then tying into asset management for supply chain management and work management to actually get the work done. And in transmission grid, a little bit different perspective because transmission tends to be more project focused in terms of you build a substation or you build a new transmission line. So the regulatory process is significantly different for a transmission project than a distribution project. But the technologies I show here are HVDC and FACS for interconnection of renewables. We are building actually a brand new factory in Huntersville, just north of Charlotte, to manufacture high voltage cables, both AC and DC, for these types of applications. Utility scale energy storage, SCADA EMS, and I've already talked about the wide area monitoring, the synchrophasers or phasor measurement units, which are what PMUs are, and also the sensor technology to capture that data. And this is the last area, which is distributed energy resources. This is an area where we're seeing more pilots and evaluation of technology rather than utility deployments. Technologies include electric vehicles, which is now gaining a lot of momentum, energy storage at the distribution level, community energy storage, distributed generation, principally PV, photovoltaic cells either at the consumer level, or we're now seeing deployments in 50, 500 kilowatts that are sitting on rooftops of warehouses and similar buildings. And in demand response, I talked about price-based or incentive-based demand response as well as direct load control. The key to remember with distributed energy resources is just because you can control a consumer load, the economic value or the monetization of the benefit occurs either at the grid operations level, it occurs in terms of the generation portfolio, which is managing the overall supply of generation to the grid and how you can offset some of those requirements. Or you may be familiar that ancillary service markets have opened up related to demand response. FERC mandated that the markets open up demand response markets where aggregators can bid in the ability to drop load as an ancillary service for operation of the grid. Spinning reserve, I'm not sure if you're familiar with that concept or not, but the grid has spinning reserve in the event that there's an interruption. They can rapidly increase the amount of generation because the challenge we have today is generation always has to match load. But if you can, instead of adding generation, drop load just as quickly, you can bid that in as an ancillary service.
Gary?
Yes?
Have the markets in the U.S. already implemented ancillary services?
Ancillary services have been in place, but now instead of bidding in to meet a requirement that's, let's say it's spinning reserve, doing that with generation, you can now do that with demand response. And that's the part of the market that's now being implemented. So those markets have been in existence, but now you can actually participate in that market with demand response. So there's companies such as Internoc, C-Power, Converge that are actually doing aggregation and bidding into those markets. So this is what the overall landscape looks like when you put all the components together. And I think the next wave of investment, once these systems are implemented, is going to be the operational technology and the information technology integration and the integration between these various applications. So what I mean by that is using smart meters to provide outage notification and service restoration verification, where you're combining the AMI in terms of the meter and the information from that with your distribution grid management. Tying distribution grid management and outage restoration with work management and mobile data. Using demand response as a tool to help you restore parts of a system that may be de-energized, where once you've isolated the faults, on a hot summer day when you're near your peak load, by lowering the demand on those feeders using a demand response program and now having more flexibility to reconnect customers. So it's how all of these systems are going to be integrated will be the next level of investment, and where I think we'll really start to capture some of the benefits from the smart grid. So just a little bit more detail on some of those. I'm not going to talk about AMI and meters, and the main reason is we don't sell those meters, so I'm not going to talk about them. They are important as an enabler for time of use pricing and some of the distributed energy resource technologies. They also can provide information, as I just mentioned, on outage notification and system verification of restoration. But I do want to talk about distribution grid management. This is a slide that I have from CenterPoint. CenterPoint is implementing a distribution management system. They are also implementing an AMI, or what they call AMS, Advanced Metering System. And they're putting reclosers out on their distribution system. About 15% of their distribution system, they're putting these reclosers, which are communications enabled, and they will be using the communications for the data backhaul of the AMI system to be able to remotely control these and automatically control these reclosers to isolate faults and then to restore customers that are not connected to that faulted section. So this is a project that's ongoing right now. We happen to be the vendor that's providing the intelligent grid, which is the reclosers, as well as the DMS software. Also, I mentioned the VoltVar controller, VoltVar optimization. And basically, when you have feeders, and this is a simplistic diagram, you get at the substation, you have a higher voltage than you do at the end of a feeder. And so utilities for a number of years have been using line voltage regulators and or capacitor banks to be able to raise the voltage on the feeder and to try and one, reduce this voltage regulation, which means the drop from the substation to the end of the feeder, and make this more horizontal. In doing so, particularly by using the capacitor banks, where you offset the inductance of motors and also the inductance of the lines, you're more efficient. Now, reactive power, I understand, is not real, but when you push back to the generation, it's real fuel that's going into those generators, and that's real capacity in those generators that are feeding those losses, those reactive losses on the distribution grid. So there's a lot of money that can be saved if you can eliminate those losses. Now, if you lower or reduce the amount of regulation, so you have a more horizontal curve, as shown here, now you can lower the voltage. And what that does is it further reduces the load on the feeders, frees up additional capacity, or requires less T&D capacity, also requires less generation capacity. And that's called conservation voltage reduction. So there's two processes. One is controlling VARs and volts on it, which is primarily related to capacitor banks, although load tap changers and line voltage regulators also come into play. And then the second part is actually lowering the overall voltage once you have a flatter voltage profile, and that's the conservation voltage reduction. There is one caveat. Does anybody know what happens to utility revenue when you lower the voltage on a feeder? It goes down. So, it's kind of a negative incentive for a utility if they're not capacity constrained to lower the voltage. And that's where regulatory policy comes into play to enable those types of programs and also to give the utility incentives to do that. Asset management, I just want to briefly show this. It's, again, the end-to-end process. Key points on this is it's knowledge of the apparatus. It's the sensors and the monitors to capture that information, get it out of the substation, archive it, and then run the decision support. And again, it's operations, impact. You want to get an alarm if something isn't working properly or is a threat to your operations. the maintenance, optimized maintenance, condition-based, life cycle management, and then recommended work execution. And then, of course, doing the actual work and managing the trucks out in the field. So this encompasses everything from transformer service and how you optimize and how you drive transformer service to get the performance out of your assets, to the decisions that you make on life cycle management, when to retire those units, when to invest, and really capture the condition and know what the performance characteristics of your T&D system are. Remember, average age of a transformer, power transformer in the US today is 40 years old. So this is becoming a big issue. So this just shows the focus on the analytics and decision support, and then that the performance models and the analytics are the key driver. So it's not only capturing the data. A lot of utilities capture data, but they don't analyze it. They don't have the resources. So unless you can automate that process and make it a systemic part of your business, you're not capturing the full value. I want to talk a little bit about transmission technologies, and one of the key areas that our company is focused on is how to interconnect renewables. And there's two challenges. One of which is shown here, this actually is China, but it's happening also here in the US, is that renewable generation normally is not located anywhere near load centers. So in China, this is a particular problem where they're developing wind to the north and hydro to the west. We have that problem here. Biggest source of wind in the US is North Dakota. Last I checked, there wasn't a whole lot of load in North Dakota. So the technologies to get that energy from those sources is a challenge. Also, if you go offshore, if you go more than 25, 30 miles, you need to use HVDC technology because of charging current in the cables. So that's why it says DC technology is the optimal choice for longer subsea applications. The other challenge with renewables is the variability. This has been floating around the industry for a while. I decided to put it in for this presentation. In that chart, each one of those lines is the daily output from a wind farm in California. Now, if you're sitting in a dispatch center and you're trying to dispatch that energy, good luck. Now, the average looks pretty good, but the individual daily curves are all over the map. So that's the challenge with wind, is its variability. Solar is in some respects better and in some respects worse. I mean, obviously, it starts to increase in the morning, it peaks, in the afternoon, and then starts to tail off. That's pretty predictable. What's not predictable is when a cloud goes over. And a PV panel can lose 70% of its output in 5 minutes when a cloud goes over. So again, from a dispatch point of view, managing that variability is an operational challenge. And that's why in many times you see renewable generation either in concert with transmission technologies, which I'll talk about in a second, or energy storage. So transmission technologies, when you have to go long distances, HVDC technology lowers losses. This is an example of what we've done in China. Just to, again, 30% losses. This is ultra high voltage. I think this is 800 kV. But you do have lower losses. You only have 2 wires. You also don't have the inductance or the effects of AC current that with the DC. So you do have overall lower losses. This is a project that was just on our webpage. I wanted to include this. This is using HVDC cables for offshore wind. It's about 100, and I think it's the mileage, it's 45 kilometers of DC cable and 90 kilometers of cable on land. This project is a $1 billion project. That's billion as in a B as in boy. That's why I included it. And what's interesting, I don't know how many of you are aware of what is the capability of HVDC technology, but you can actually use the analogy of an extension cord for a nuclear power plant. 2 cables, this big in diameter, you can move, I think we're now up to 1,200 megawatts of power. That's 1.2 gigawatts. 2 cables about this big in diameter. Amazing technology. $1 billion to go 135 kilometers. Wind. You saw that chart on the output of wind. That variability can cause operational problems. So one solution is to use static Var compensators, which are power electronics, which can support voltage through the control of VARs on the transmission grid. So we're implementing those technologies in Texas as well as in some other areas. But what static Var compensators do is address one of the 3 limitations in power transfer across a transmission line. So 3 limitations as to what prevents you from moving power across the line. The first is the voltage regulation. You can't have the voltage at one end significantly out of whack with the far end. So if you have too much voltage regulation, that's not a good thing. The second limitation is thermal. You can't heat up the wire so much that it sags and touches a tree, which may cause a major blackout of the Northeast. So that's the second. But the real constraint on transmission lines has to do with the stability of the grid. The grid operates based on what's typically an N-1 or N-2 contingency, which means the grid has to remain stable if any part of the infrastructure trips off or is otherwise compromised. If you have too much power going down one transmission line and you lose that transmission line, you can lose the stability or have an unstable grid. That's the main limitation. And what a static Var compensator does is it relaxes that constraint. By being able to provide voltage support, you can actually transfer more power down the grid. Series capacitors. These just allow more transfer capacity by reducing the inductance of the line, so you get more throughput. This is on a fairly long transmission line in Texas. We've also have deployed these on some of the longer transmission lines out west. And so now I want to talk about virtual power plants and distributed energy resources. So this just shows schematically looking at different areas of a service territory and some of the different types of technologies and controls that would be implemented. So you may have direct load control, which is shown here. You could have distributed generation, whether it's wind or solar, electric vehicle charging, critical peak pricing in one area. It could have just a pricing program in another area, or you could have, again, renewable generation, energy storage, electric vehicle charging, etc. Or these could be distributed throughout the service territory. What the virtual power plant does is it aggregates, forecasts, and can manage these distributed energy resources spread out through the service territory. Now this slide is pretty simplistic. The actual process is a lot more complicated, and this is a schematic of the software that we use to do that. So part of it is the customer process, customer registration, doing billing determinants, managing and aggregating the customer side of distributed energy resources, and managing in particular, as shown here, demand response. The second part is tying that into distribution operations, which is shown with the distribution management box at the top. The third is how you, again, monetize the benefit of having distributed energy resources, which is your generation and energy management, or your generation portfolio optimization, which is shown in the middle. And then the last function is the commercial process. If you want to take that virtual power plant and that portfolio to a market, there's a commercial process associated with bidding into the market and getting paid from the market for the services that you're providing. But the concept of a virtual power plant is basically that aggregation of distributed energy resources, and in being able to use that as part of the generation portfolio, or bid into a market such as the New York ISO, ISO New England, PJM, and some of the other markets. This is demand response. This is a program that's actually being implemented at OG&E. And what they've done is, during their peak, which they defined as from 2 to 7 p.m., they've implemented various pricing. So 4.5 cents is their base load. And then during that peak, they raise the price to 11 cents. If it's a little bit more severe, they go to 23 cents. And then if it's real critical peak pricing, they're at 46%. They did a pilot in Norman where they encouraged consumers to participate in this with the understanding that there would be technology to control the loads in their home based on what the price is. So this is the result that they got. The immediate conclusion that they made is that, contrary to a lot of studies, there actually is price elasticity of electricity. People actually will respond. Now, what's on the right side, PCT is programmable communicating thermostat, smart thermostat. IHD is in-home display, providing information to the consumer with an in-home display. Web is a web portal where there's information to the consumer. And then all is all of the above. And you can see that the biggest impact is with the thermostat and all of the above, which is really related to the thermostat. But even with just providing information and having this price structure in place, they did get an impact. Now, when you lower load by this much, this is about 1.6 kilowatts, which is pretty significant. You can make an impact through demand response programs on the consumer, residential consumer peak load. In this case, again, they were using pricing. What we have seen at other studies is those programs where you sign up to participate in a demand response or a load control program where you allow the utility to control your air conditioner, as an example, hot water heater, and pool pump. We have seen that customers typically save, without any change in rates, no change in rates, customers typically save in the range of 10, 15, maybe 20% based on going into a web portal and programming, I'm not at home from 8 to 5, therefore, raise the temperature in my house if it's the summertime, schedule my pool pump so I don't accidentally leave it on, so that it only runs the minimum number of days that I need in order to keep my pool clean. Control my hot water heater, no sense in heating that water all day if I'm not even home. So by going through that process, which is a sustained process because it's programmed either into a thermostat in the case of OG&E or programmed into a web portal using other technologies, it is sustainable, which is good. The benefit to the utility is with these types of programs, somewhere between 40 to 60% of the customer's contribution to peak load is controllable by the utility. Now, if you recall in that one chart early on, I said FERC predicted that 20% of the load would be controllable if demand response was rolled out. But what utilities are seeing that are doing pilots in this area is somewhere between 40 to 60% of the in-use customer's contribution to peak load is controllable, which is huge. And when you think about the value of that from generation capacity, T&D capacity, that's why Wellinghoff, the head of FERC, he actually views demand response as cliche, but as the killer app. Particularly now when you can also control electric vehicle charging, for example. So, demand response. Energy storage. We're now seeing energy storage move from feasibility and pilots actually into grid deployments. These two pictures on the left are actually a battery energy storage facility that our company did up in Alaska. 40 megawatts. It's a 40 megawatt battery. So there's close to 14,000 batteries, 2.5 by 2.5 by 2.5 cube. So it looks like a big airplane hangar. So this shows the rows of batteries. This shows the converter. On the right is what we're doing today. We still can do the one on the left, but what's on the right is the modular approach that we're now taking to battery energy storage. So in a container, we can put the power electronics, the converters, we can put the controls, and depending upon the size, we can actually put the power transformer in what looks like a shipping container. Obviously, it's modified for the application. The batteries, depending upon the size, can either go into that container or they can go into a second container which would house the batteries. So these technologies are feasible. The car industry is doing a great job at driving down the price of lithium-ion batteries. So that's helping the utility industry. So batteries can do a couple of different things for you. The one in the system that I mentioned that we installed in Alaska, there's a loosely connected transmission grid. And if there's a disturbance and the grid loses stability and customers lose power, their homes will freeze in about 30 minutes. So that system provides additional support to the grid, eliminating the need for diesel spinning reserve, which burns diesel gas and creates emissions. So it falls into this minutes category. So it can put out 26 megawatts for 15 minutes or 40 megawatts for 7 minutes, in that range. You can also provide in the seconds, you can provide also flicker compensation or voltage sag correction. But the other main application of batteries, particularly for community energy storage, is load shifting or peak shaving. Possibly you could use it for energy arbitrage. We're not seeing it. But this particular application here, you're addressing one of the biggest operational challenges we have with the grid, which is always matching generation to load. With that application on the right side, you now have, to some extent, decoupled the generation from the load, and it gives you more operating flexibility. We're doing some work with General Motors to repurpose Chevy Volt batteries. Anything GM can do that can lower the cost of the batteries in the vehicle, such as having a residual value to use them on the power grid, they're very interested, so we're looking at them for the energy storage. Now again, on that previous slide I showed power on one axis and energy, or the energy storage capability, at the other end of the spectrum. In the vehicle, it's all about power. And even though the capability of the battery degrades to 50% of what it is new, on the power side, it still has probably 75–80% of its capacity for energy storage. So we can capture that value and repurpose the batteries. And then the other thing that we're doing with electric vehicles is looking at the charging infrastructure. If it's during peak load, perhaps offsetting some of that with energy storage. But how do we manage the grid when we have different types of electric vehicle charging? So can we use renewables? Can we use energy storage? There's different types. There's level 1, there's level 2, which is 110 volts and 220, what you might use in your garage. But then there's also fast DC charging at 480 volts. So we're looking at this holistically in terms of how you manage the grid, how you measure and control electric vehicle charging. Because there's two issues that the industry is facing. One is, if you have a large concentration of vehicles, you don't want all those vehicles on a feeder to arrive at the house or houses at 6 p.m. and all of them connect. So you can shift that load, and this was a study done by EPRI where the green curve means the green curve is shows the base load, but the red shows if you do nothing, you just allow those vehicles to charge as soon as they arrive. But you can shift that load as shown with over on the right side of the curve with the blue line, and I guess it's also the green line, either through time of use rates, where you give customers an incentive to delay charging until 11 o'clock, or you directly control those loads through smart charging. So from a system point of view, electric vehicles aren't going to be a problem anytime soon. We can shift or defer the load unless we have huge clusters of vehicles that are charging in the middle of the afternoon, which may happen at employers or other public places. And there, utilities are going to have to treat that just like any other commercial load. The other challenge is known as the last mile, or the clustering impact, where if a person buys an electric vehicle and all his or her neighbors get real excited and they go buy their own, and all of a sudden you have that coincident load on a single distribution transformer, you can overload it, which is what this shows. The darker line is the actual load on the transformer from residential use. The red line is electric vehicle charging using this scenario as defined. And then the right is the combination of those two, and you can overload a distribution transformer. That's good for our business. We sell those transformers, so we're looking. I just wanted to include this slide. This is a project that we're doing over in Europe, specifically in Sweden. at Royal Seaport. One of the things that we find with Europe is one of the major drivers there is emissions and carbon footprint reduction. And that's really a key driver behind this project. But this integrates a lot of the concepts and technologies that I've been talking about. So smart homes and buildings in demand response, distributed energy resources, PV and wind being integrated, also incorporating home and building automation, EV, electric vehicle charging, incorporating electric vehicles, energy storage. But a big part of this is what they call the harbor control solution, and that's shore-to-ship power so that they don't have diesel generation on board ships generating power for the ships while they sit in the harbor. So now they're looking at, can they use grid power, particularly with the renewable mix, to feed those ships that are in the harbor. Automation of the substations, and then there's a lot of research and development surrounding this project, looking at individual consumers, their consumption patterns, their carbon footprint based on the type of energy that they used. And this is currently going on, again, as I mentioned, in Sweden. So these are my wrap-up slides. People are investing money in smart grid. This shows the market size. Today, AMI got off to a fast start, but it's going to fade and peak at probably the next year. The next wave will be distribution automation. It's probably going to peak around 2015. And in the slower growing and more sustained investment areas are in transmission, asset management, and demand response. So all the technologies that I talked about focus initially on AMI, particularly with the funding. A focus on distribution automation, where utilities can drive reliability and efficiency. And then we're seeing demand response increase, asset management increasing in a big way, and also transmission upgrades. Where does the smart grid value come? This is a slide from McKinsey, and they estimated if the industry rolled out smart grid across the United States, it would save $130 billion a year. A lot of it is in terms of grid applications, with the biggest piece being volt-var control. But the other big piece is in the customer applications, which are driven around peak shifting, energy conservation, and avoided cost of capacity, particularly with generation, but also there's a factor in there on T&D. Now, total revenue for the industry is about $390 billion a year. So if we were to fully roll out smart grid, we could save about a third of what we're currently paying for electricity. And so the question is, well, why aren't we doing it? And that's a policy issue. It's a challenge for funds. It's vetting the technology, because utilities typically don't invest in anything new. But the economic payback is there if these investments are made. For those of you still in college, the students here, jobs. KEMA did a study for the GridWise Alliance and looked at the job impact. And so their estimate, based on what's being done today, is smart grid will create 140,000 jobs. The bulk of them will be with vendors like ABB, direct utility suppliers. So this is having an impact. It does negatively impact some of the utility jobs. Probably not a good career choice to be a utility meter reader these days. But there is job creation associated. And then this is my final slide. I don't know how many of you recognize this, but you are in the smart grid hub of the world here in Raleigh. We have an amazing concentration of companies and technologies here in the Research Triangle area. Our company, obviously, some of our competitors, meter manufacturers in terms of Elster and Sensus, and Itron has a facility here. SAS is doing work in the smart grid, Accenture, IBM, and so on and so forth. So this was something that was put together by the Raleigh Chamber. There was a Duke study that looked at the concentration, and ourselves, along with other companies, are looking at the regional economic development associated with these companies, but also what's equally important is the university support and we also need the government support. And with that, we do truly believe that we can create here in this region the global smart grid hub for driving technology. We're working with the Freedom Center with some of our work because we're also co-located here on the campus. We're building a center of excellence for demonstrating smart grid technologies and are doing collaboration with Alex's organization. So we're pretty excited about smart grid for all the reasons. And with that, I'm done, although I did go 2 minutes over time. But I can hang around if there's any questions.